I appreciate the opportunity to moderate this panel, and I appreciate all of the panelists here. Their willingness to share their expertise and talk with you all today. So we've got from left to right here, we have Natalie Ballew from the Water Development Board. Appreciate you being here, Natalie. We've got Andy Donnelly from Daniel B. Stevens and Associates. Appreciate that. And then John Ellis from the U.S. Geological Survey. And appreciate all of you being here. So as Leah mentioned, the topic today is GAMS, or groundwater availability models. GAMS, the next generation, is our title here. Our objective, though, is to explore efforts and opportunities for updating the groundwater availability models and get into the benefits that those updates can have for the joint planning process and for groundwater management, groundwater management decision-making in general. So before we move into the questions, I have just a brief bit of background for folks. When we talk about groundwater availability models, that's, in my mind, or for at least the purposes of our discussion today, it's a particular subset of groundwater models in general. So when we talk about GAMS, we're talking about the groundwater availability models that are considered the model of record at the Texas Water Development Board, and that are used for many different purposes. When they originally came out, they were used to help us understand the aquifers for folks like me and other folks, both on the call and on the panel. When you develop groundwater availability models, you have to assemble a ton of information and try to get it to work together. So one really important piece or benefit of groundwater models is that it helps us understand the aquifers. They're used for information that goes into GCD management plans, as they're used for the development of desired future conditions. That's known as the joint planning process. And then the Water Development Board uses it to estimate modeled available groundwater. And they're also used not just at the state level, but they're used by GCDs for evaluating permits and for other uses that I haven't listed here. But we're talking about the model of record models at the Water Development Board. We're not talking about site-specific models or outdated models or other things. So I want to draw that distinction here. So with that said, Natalie, the first question's for you, and you're at the Water Development Board. Could you provide us with an overview of TWDB's current and upcoming efforts to update the GAMS?
Certainly. So before I get into the GAM updates, I would like to just throw it out there that the Water Development Board has a 2021 to 2025 strategic plan, and groundwater science initiatives are part of that plan to further groundwater science through aquifer storage and recovery studies, brackish groundwater, and of course, GAMS. And we actually also got some legislative appropriations to fulfill those initiatives, which is great. And Director Pop also mentioned a bit about those ASR and BRACs, but I bring it up here now because I think that some of the things we're going to be talking about today in terms of GAM improvements in the next generation of GAMS can eventually go and overlap with the ASR and BRAC studies that we do. So our GAM program, Wade, you gave a wonderful background to it. It's been around for about 20 years. And like Wade said, the purpose of them is to provide reliable tools to water resource planners, decision makers, and whoever wants to use them to assess aquifer responses to groundwater use over time. And we consider these models to be living tools. So if there's new data available or we understand the aquifer a little bit better, we are able to go in and update the models with that increased understanding. So we're required to have models for all major and minor aquifers in the state. And we're almost there. There are 3 minor aquifers that do not yet have models, but we are working on them. And currently we have 7 models that are in the process of being updated. So these are models that already existed, but we're in the process of updating them now. And so what happens with those updates? One of our biggest priorities right now is to upgrade older models into newer code. So some of those older models are in code that's no longer going to be supported. So that's really our focus. But while we go through and update these to the new code, we are also able to incorporate new data that we have that reflects a better understanding of how an aquifer behaves. And a lot of these models also are incorporating a component so that we can better see what's happening in the groundwater surface water interaction world. And one of these models is the regional Edwards Trinity Plateau Aquifer System model. So it's a whole handful of different aquifers. But really the reason we're lumping a whole bunch of aquifers together into one model is so we can really understand how those aquifers communicate with one another. And part of that project as well includes a research component to get a better understanding of pumping and recharge in the study area, but also for groundwater and surface water. So we hope that we can have that kind of accompanying research to go through with all of our other models that we update in the future. So after we finish these models that we currently have in progress, we're going to be about halfway done with updating to newer code. And hopefully for the rest of them, we can start to incorporate some of the improvements that we're going to talk about today.
All right, thank you, Natalie. I appreciate that. And that actually leads pretty cleanly into our discussion about groundwater availability model improvements and some ways that we're seeking to improve these tools. So John, the first question on GAM improvements is going to go to you, and it relates to cell size. Cell size is something that's inherent to these groundwater models. That's a decision that's made early on in the process. But could you describe for us why cell size matters and how it impacts how a model is used?
Yeah, sure. Wade, can you hear me okay?
Yes.
Great. So I guess starting off first, I don't want to encroach too much on kind of the discussion of boundary conditions, because I think we're going to get to that here in a bit. Obviously, cell size and boundary conditions, they do go hand in hand. So I'll try to kind of work my way around that discussion while discussing some. And I guess you could say as a basic premise, you could say kind of the size of cells determines the extent to which hydraulic properties and stresses vary through the model region. Hydraulic properties and stresses are, they're specified for each cell. So the more cells you have in a model, the greater the ability to vary those hydraulic properties and those stresses, right? So if the cell size is too large, you could say, important features of the framework might be left out or just, poorly represented. With that said, if you go too fine, there are practical limits to going too small, which, I mean, anybody that's worked with a model at 20, 30-hour runtime knows well that it doesn't usually work well. And, you pay the price for that computational burden in terms of the amount of time to complete the model and the project. So there's kind of a sweet spot there somewhere between, too much and too little. And I think it's important to evaluate, the known or the assumed variation of hydraulic properties and stresses of the system that's being simulated and kind of compare, to the size of the cells. And, the intended use of the model and the importance of the features being discretized, it affects the, the evaluation of whether the model is discretized appropriately and whether, important features are missing that would cause kind of a systematic error or a bias, if you will, in the simulation results. So, again, I don't want to go into, other discussions, like groundwater surface water interaction too much yet here, but, cell size does have a strong influence on simulating, say, stream flow. If you're using the river package, the simulated river, of course, occupies the entire cell. So in a regional scale model, like many GAMs are, there can be a substantial mismatch between the actual river width and the underlying grid cell, which creates errors, in the simulated water table and then, in seepage as well. So there's that consideration. And, another consideration there is having, sometimes a coarse vertical discretization in the model to avoid, the bane of model's existence, which is sometimes dry model cells. So you might have to simplify the geologic features vertically when you're taking that approach, which again, in some cases may not work as well as you need. I mean, yes, you have the highest active cell available in that option, say the recharge package, and then you can do cell re-wetting and it mitigates that somewhat, but then you get too many dry cells or too many cells drying or re-wetting, then you get convergence issues. So of course, all this ties together a little bit. So horizontally large cells might disrupt the continuity of kind of your geologic deposits that you're trying to simulate. You can get isolated cells and maybe breaks in channels with high conductivity. So of course, again, there's a fine line between going too coarse or too fine here. So just to note on methods, I mean, you can use local grid refinement in an area where you really need to zoom in, or you have a lot of fine-grained detailed data, or even an inset model, which is typically not done for GAMs, but there's, you know, that's an avenue, or you could use variable grid spacing. Now, to note with model advances, which is part of this discussion, kind of centered on it, is you know, now with ModFlow 6, with that new core code, you know, ModFlow 6, the 6 being the 6th iteration of the core code, you have some new options that are available. Horizontally, you have greatly expanded options with that unstructured grid option. I mean, you can use that DisU package, and you can do triangular hexes, hexagonal, quad patches. There's any sort of combination you can do there that really will greatly expand, you know, the flexibility in the model. And vertically, you can use vertically staggered connections, you know, whereby cells can be connected to more than one cell in a single horizontal direction. So with the newest, most current code being ModFlow 6, you have these options that you really didn't have before. And again, they're there to add resolution areas of interest versus having to go, you know, the telescoping model within a model, or using local grid refinement. So this is just some of the flexibilities offered with the newest, most current code.
John, I appreciate that, and not to editorialize, but your eyes lit up when you started talking about all the capabilities of ModFlow 6. So
yes, I know. It's I watch out there.
so Natalie and Andy, do you guys have anything to add on cell size before we move on?
I'm going to be touching on that a little bit when we talk about groundwater surface water interaction, because that's a lot of what we're going to be looking at. So
okay, well, thanks. Well, I appreciate the transition, Andy. So, you know, GAMs do have a number of ways of handling groundwater surface water interaction. And so how is that model information used, and why is groundwater surface water interaction something that we've already mentioned several times today? Why is it such a focus area for improving the GAMs?
Well, it's become a focus area not just for improving the GAMs. It's kind of become an important topic in hydrogeology in general. I think because traditionally groundwater and surface water have been treated separately, and people have come to realize that they really are fundamentally interconnected, and that they form a single resource. Sometimes that interconnection is very dynamic, like with the Edwards and Trinity aquifers, other times less so, but they're still interconnected. It's important because we've got a projected growth in water demand over 50 years in Texas that's pretty significant. And because of the interconnection, what happens with one impacts the other. So we realize as we start to develop groundwater resources, for example, that has the potential for impacting surface water resources, which is important because people rely on those surface water resources for water supplies, as well as there's an environmental consideration because surface water serves various ecosystems, such as freshwater discharge from rivers into bays and estuaries along the coast. Now, groundwater surface water interaction and GAMs have typically been incorporated using standard ModFlow packages. John mentioned a couple: the river, stream, drain, reservoir, among others. These are head-dependent boundary conditions shown here. The water level in the cell is calculated and compared to the water level that's specified in the surface water boundary condition. And depending on which head is greater than the other, the water either moves out of the stream and into the groundwater budget, or out of the groundwater budget and into the stream. These packages really just give a very rough approximation of the groundwater surface water interaction. It's really just kind of a first order approximation. If we go to the next slide, we'll talk a little bit about what some of the GAMs are doing. It's important to understand that, to understand some of the spatial groundwater flow systems that exist. We have small, localized flow systems, as shown in the top there, where groundwater or water infiltrates into the surface, hits the water table of an unconfined aquifer, will move vertically and laterally, discharging in the order of days, weeks, months, or years into topographically lower areas. On the other end of the spectrum, we've got groundwater that migrates vertically through multiple aquifers and confining beds over hundreds or thousands of years in these big regional flow systems. And we kind of have everything in between. It's a spectrum. So we have intermediate flow systems, which are in between local and regional. And this is important in the GAMs because the GAMs are regional models. They typically have had 1 mile by 1 mile grid cell sizes. They treat aquifers all as one in a single layer. And so a lot of those localized flow systems just can't be incorporated into a regional model with that discretization, with those big grid sizes, with those big vertical layers. That's important because those localized flow systems may be a pretty significant contributor to surface water, groundwater surface water interaction. So if we'll go to the next slide, some of the things that are being done, that started to be done over the last 10 to 15 years. This is from the new central Queen City, Sparta, Carrizo, Wilcox model. We're starting to introduce some additional layering to try and represent the shallower flow systems. Here, the blue is a layer specifically for the Colorado River alluvium in this particular figure. There's also a second layer in the light green that represents the shallow flow system, and that has been put across the entire model domain. Whereas previously, the darker green Carrizo would have extended all the way up to the surface and been interconnected with the river. So this allows for a little bit of the regional systems to be a little bit more isolated from direct connection with the rivers, and also allows for a little bit of that local component to be modeled. If we go to the next slide, and this was shown earlier. Nope. Well, the unstructured grid that John showed earlier allows for the refinement, the lateral refinement of the grid around those surface water bodies that you're particularly interested in. And lastly, and I put this slide in here because when we first started talking about groundwater surface water interaction, there was a note on there about linking WAMs and GAMs. My first thought was, wait a minute, we've kind of covered this, and then I realized that was also quite some time ago, back when I was at the board. I was a contract manager for a contract that did explore the possibility of linking WAMs and GAMs. That was done by HDR. If anyone's interested, I think there is a report on the Water Development Board's contracted report site. No, go forward, go back, please. Basically, in a nutshell, although they sound similar, WAMs, water availability models, GAMs, groundwater availability models, and they sound similar and they should be able to be linked, they are very fundamentally different models. And that report sums up very well why they are very different models. And I think they kind of came to the conclusion that it's going to be difficult to link those. Time steps are different. WAMs are monthly, GAMs are typically annually. The model simulation, WAMs are retrospective. They look back at what would have happened in the past if this had occurred, whereas GAMs are calibrated models where we apply conditions and do predictive what would happen in the future. So there are a lot of basic differences, but the WAMs and GAMs, I thought it was important to mention. Really, probably not something that we're gonna see soon.
Okay. Andy, I appreciate that. Natalie and John, do you have any additional thoughts on the groundwater surface water interaction that Andy discussed? If not, I'll move on, because Natalie, you mentioned innovative water sources like brackish groundwater. I believe John did as well, and this actually links up with something that I've observed in my time doing Texas groundwater work, which is as we go through and as we're improving models, we find new ways to use them. And so brackish groundwater, we have arrived and finding new ways to use that. So I'm curious from your perspective at the Water Development Board, how does the emphasis, relatively new emphasis on innovative water sources, in particular brackish groundwater development, impact and inform how future models are developed?
If we could proceed forward 2 slides, that'd be great. So one thing to consider when we're talking about BRACs and GAMs is the purpose right now of those 2 programs. So the BRAC's purpose is to map and characterize brackish groundwater resources throughout the state and really find like those sweet spots of brackish groundwater where you can get the highest potential for long-term productivity, but also have the lowest risk of any negative impacts. Whereas the GAM, as we've already discussed, is regional scale modeling to support state water planning. So BRACs is a little more detailed, localized study of geologic frameworks and water quality, and GAM is more regional in scale and has a more general application. I'd also like to say tune in tomorrow to hear a little bit more about BRACs programs, Erica Mancha in the afternoon. So while the scale and the intent of these 2 different programs and the scale of the studies are different, there is the potential to feed in information from BRAC studies into GAM geologic frameworks and other components from BRAC studies to feed those into the GAMs. So why and when does it make sense to incorporate BRAC's info into GAMs? I think first off, you really got to think about the purpose of the model. We're talking about regional joint planning models for this panel, but you also mentioned, more localized models and kind of nested models within regional models. So really think about this, what the intent of the model is. Another thing is that the brackish groundwater program, they map water from 0 milligrams of total dissolved solids all the way up to seawater. And our major and minor aquifer boundaries, which are what the GAM model extents are typically based on, those do not go all the way up to seawater level salinity, but some of them do incorporate up to about 5,000 milligrams per liter of TDS. So currently, some of the GAMs already incorporate brackish groundwater, but there's no way to distinguish the brackish from the fresh water in the models as they're currently set up. We do have one model that is the Lower Rio Grande Valley model that incorporates water quality transport modeling into it. But in order to do that with all of our GAMs, we need a lot of detailed data to put in to get that water quality modeling going. Perhaps with this new code and the unstructured grids, we could refine grids in brackish production zones where the BRACs program has identified those zones, and we could refine that based on the studies that they've done. We'll see how that goes. So this could improve decision making, first off, because BRACs has really detailed data and their studies are fantastic. And if you have a better understanding of what that framework is and where that water quality is, you're automatically have better informed decision making. And this could also help in terms of joint groundwater planning and districts who are looking to establish brackish groundwater desired future conditions. If we had that ability to model water quality, we would also be able to give a MAG for brackish groundwater. And we're currently looking at zones where the brackish groundwater zone overlaps with a MAG zone. So that'll kind of give us a better picture of where the overlaps currently are and where maybe the GAM doesn't actually extend into brackish groundwater areas. So for any of this to actually happen and incorporate BRACs into GAMs, first off, we need that detailed mapping from those BRAC studies, and that has to go into the GAMs, specifically in the down dip formations, because we just don't really look at that with the GAMs as they currently are because it's outside of that aquifer boundary. And you'd also need to incorporate water quality component. And I've never done that before, but I've heard it's a challenge to accurately model density differences in models. But I think that as a starting point, taking those brackish groundwater studies and feeding that data into GAMs for the geologic framework during conceptual model development, that'd be a good starting point.
Yeah, those are really important points that you made there, Natalie. In particular, the link between, you know, the freshwater portion that the GAMs are really focused on right now versus using the more brackish components. And then, you know, as you know, we do joint planning work. I think about what's the potential impact of brackish development on the freshwater resources, or vice versa. You know, you'd hope that there's minimal, but you know, you don't really know until you evaluate that. Andy and John, do you guys have anything to add on that before we move on?
No, let's move on.
Okay. Okay. So the next piece is a topic that is going to make at least half of the audience uncomfortable here, and it relates to model uncertainty. It's something that we know intuitively. It's something that we talk about occasionally. That models aren't perfect, but you know, you hope that they're useful. And so from my perspective as a modeler, this is something that I spend a lot of time thinking about. And John, this question's going to you because I know that you have been and are working on model uncertainty, because you know, characterizing and understanding uncertainty is, in my mind, something that, or an area of modeling as it relates to the GAMs that's ripe for improvement. Could you briefly describe what we mean when we talk about model uncertainty, how we quantify it, and how it can be used to inform groundwater management?
Yeah, absolutely. Thanks, Wade. And I'm glad we're not immediately after lunch, because this tends to put the other half of the people that Wade didn't mention to sleep, being uncertainty. So either I'm going to scare you or put you to sleep, but I will still try to trudge on and do my best. So to know, you know, there's a lot of assumptions that are made when you're constructing a groundwater model used to simulate a natural system, of course. And each of these assumptions results in uncertainty, and uncertainty in the model is, of course, propagated through the model results and then through the scenarios, which are usually the end goal that you want out of a model. I mean, a model is not ever just an end goal in and of itself. I mean, the purpose of it is to run those scenarios and look into to answer the question of what if. So, you know, through the process of inverse modeling, you know, whereby the parameter values are estimated from a limited amount of data, you know, it produces non-unique solutions. So the scenario outputs can be viewed as more what you could call probabilistic than deterministic, and they have a range of possible solutions, even if you're only running one model and you only have one answer. So, you know, uncertainty can be, as Wade mentioned, a bit of a dirty word regarding groundwater models, especially those that are used for regulatory or water management purposes. I mean, you know, these regulatory purposes, you know, they're run to produce a single number or a specific outcome. But, you know, for a model to be most effective in a decision support role, it's helpful to include the reliability of that simulated outcome. And that's where uncertainty approaches, uncertainty quantification come into play. So more recently, there have been what we call ensemble-based approaches. These have become more common, although they've been used for many years. I mean, for 20 plus years. But now we have more of the code and the software to do it in a much easier way. So when I say an ensemble-based approach, what I mean there is, you know, rather than run a single model, you run a parallel set of models, each with a kind of a stochastic set of model parameters, you know, the things you tweak in the model. And these are within a user-specified upper and lower bounds that, again, you can set based on expert knowledge of that system. So typically, you would do this. You would apply this, you know, this approach to the calibrated model for scenarios with forecasted interests that are important, you know, to the project or the objectives or whatnot. But now we can actually take that a step further, and you can implement this from the very beginning of model calibration. Rather than just performing it on the scenarios after model calibration is done. So there is a new code from Jeremy Wyatt called PEST IES that is it's a recently published code and allows you to do what I'm mentioning here with very minimal changes to the way you would typically do model calibration. You know, groundwater models typically don't like to always change their methods every year and readapt to a completely different set of tools. And here, this allows you to avoid having to do that. Again, there's not a whole lot that is different from what you would typically do if you're, say, using PEST, you know, i.e. parameter estimation calibration software in your setup to do model calibration. So what you can do is in running this ensemble, you can select, say, a central tendency model as your single model, that regulatory answer, and you get that single result while you wrap it in the context of the uncertainty quantification that you get from the ensemble. So you get kind of what I would call the best of both worlds. You get the single answer, but you also get it wrapped in the uncertainty associated with it that you can quantify with that ensemble. And again, if you're already using the PEST code, there's not a whole lot different that you have to do this. So there is actually a real world published example that did exactly this in February in Frontiers of Earth Science. So there is a real world example. It's out there on the street. So that this has actually been used now, and it's getting adopted more and more. So I think, you know, this approach, hopefully this will bear fruit and can get slowly introduced into the, you know, the regulatory regime, so that way you can see the uncertainty while still getting at that single answer that you're looking for and that you want. So I think that kind of encapsulates it.
I appreciate that, John, and we didn't really talk about this hurricane chart here on the slide, but as a Houstonian and someone who had we had kind of an interesting week last week trying to decide where Hurricane Laura was going to go. Have this hurricane slide up here to relate into uncertainty, because models can be uncertain and they can provide kind of fuzzy answers, in particular in the long term, and still be useful for decision making as we decide, you know, when it comes to hurricanes, whether we're going to stay or whether we're going to go, and that kind of thing. And while I think the groundwater modeling piece of it probably doesn't have quite as fun and graphics as Getty models, the same concepts apply on that. So appreciate that, John. And John, I'm actually going back to you as we transition out of, you know, specific opportunities for updating the GAMs versus the use of the models, because a common thread of our discussion today is that a model can't be all things to all people, or at least that's my summary of it. So you have developed models, I know you're currently in the process of developing at least one model. Could you describe a bit how the modeling process itself and the decisions that you make during the modeling process affect how that model can or should be used in the future?
Sure. So with that, I think we're kind of heading towards kind of discussion of boundary conditions, I think is what I'm hearing you say there. So, the boundary conditions, in the model determine kind of where water enters and leaves the model, of course, right? And, there's, you have everything from lakes, streams, recharge, ET package, and wells. And as Andy mentioned before, you have the 3 different types of boundaries: specified head, specified flux, and kind of head-dependent flux there. So you have to think carefully about those boundaries that you choose in your model, because they obviously have a large impact on your results, as both Andy and Natalie mentioned. And it's that conceptualization is very important, because you can have all the bells and whistles in a model, but if it's not conceptualized correctly, I mean, as they say, garbage in, garbage out, which may be a bit of a harsh term and not one that any of us ever wants to use with a model, but I mean, the basic factor remains. So I would say that, related to what Wade is bringing up there, I would say that relates strongly to boundary conditions, and I think they're critical to development of a good model. So I would say, defining the uses of a model, and especially the appropriate uses of a model, are key to this. And, it's what drives the use of certain boundary conditions, based on that conceptual model that you come up with, that you look at, whether it's a geologic framework, hydrogeologic framework, or whatever is appropriate for your system. So, a model of a particular area developed for one study with a particular set of objectives, it may not be appropriate for use in another study in the exact same area. I mean, we do see this, especially with, if you wanted to compare WAMs and GAMs in the same area, you'd see they're different objectives. Even if they sound at first blush, they sound the same. So if the model is intended to forecast, say, the response of an aquifer to additional withdrawals that might affect the stage of surface water bodies in the area, then simulating, a lake with a constant head, it's probably not going to work very well. It's probably not an appropriate boundary. You would need something more complex. And another example would be, say, using a specified head boundary at a location where there's no source of water to maintain the head at that value you specify. the appropriate to that boundary, you can actually test that by evaluating the flow from that boundary and changes due to flow from parameter values and whatnot, or stresses within the models. You can actually evaluate this and look and see is what I'm doing there appropriate in some cases. And you know, if a stress changes, or if the stress causes a large change in flow at a boundary, then you know that means the head's probably changing there, and you probably shouldn't fix it. So you know, artificial boundaries can apply, you know, if they're applied improperly and not evaluated, can overly constrain the response of the system and create biases in the results. So, you know, one of the more important boundaries in a model is, of course, you know, the recharge applied to the top boundary in the model. And traditionally, this has been done a number of ways, but newer codes have improved on what we've done before. And you know, example of that is the soil water balance code to produce spatially distributed estimates of recharge. You know, applied through the recharge package. And maybe that is a better way to determine recharge and apply it to a model area, especially if you know it's a regional scale model and it combines multiple types of geologic units versus just that single value, just apply it everywhere, throw it in your calibration and move forward. So there are some new advances in technology and modeling technology that we can use and we can apply to these models that may be more appropriate or a better solution.
Okay, appreciate that, John. And Andy, this next question's related, but it's going to you. So John was touching on boundary conditions, and if we take a step back from that, you know, there are decisions that are made during the modeling process, or there are features that are just inherent to models that create model limitations, like what John was talking about. Could you discuss the model limitations in general, and you know, those that are inherent and those that you know can be managed through development?
Sure. I mean, this will be a little repetitive because John has touched on several of the things that kind of also apply to limitations. I mean, models just inherently are simplified representations of more complicated natural systems. In this case, we've got a numeric representation within mod flow of much more complicated aquifers and groundwater flow. It's important to remember that models don't give you the answer. I like to say that models give you an answer. It's easy to get fooled by, you know, the results of the model where you get nice water levels for each cell. You can draw nice water level maps to you know, results to 4 decimal places. But you know, it's important to recognize that there's uncertainty and there are limitations to the model. All models have limitations. Model reports, all the GAM reports will have a section discussing the limitations that should be read and understood. In general, there's sort of 3 general categories of limitations. You got data limitations, you've got limitations of the model, both the conceptual model that you develop and then the numeric model you develop. And then also limitation on how you should use the model. Data limitations, this is a figure that I pulled, this is a figure I pulled several years ago. This is from, I believe, the first Northern Trinity GAM, showing the distribution of wells with which you could make storage estimates for the entire Northern Trinity model. And so you've got multiple layers across that entire green and purple area where you're needing to come up with storage estimates, and those are the wells that you have data for it. Hydrogeology, we just have to face the facts that we often have very sparse data availability. You can't generally see an aquifer. You can look at it in individual well bores. You can measure certain properties. There are other parameters that you really can't measure. Recharge, evapotranspiration, groundwater surface water interaction are difficult to directly measure. So as part of the process of putting together vast arrays of data for your model, you have to make a lot of assumptions, and assumptions are inherent in the process. One of the big issues in Texas that we have is the uncertainty pumpage, historic pumpage. That's a huge issue because that pumpage has such a significant impact on the resulting groundwater model and how you're trying to calibrate your model. These data limitations may also limit your understanding of the aquifer and the conceptual model you put together of aquifer flow, how the aquifer functions, how the different boundary conditions play in there. The lack of the data may limit that conceptual understanding of the model. And then also the model that you actually put together, the numeric model that you construct will have limitations just based on how you construct it. Again, they're simplified representations of the natural system. You're putting together grid cells that might be a mile by a mile. You've got a lot of lumping and averaging that have to go in there. Each data point may not be specifically represented if you've got 2 or more data points within a model cell. Groundwater surface water interactions are very contingent on some of the elevations you use, but if you have to use an average elevation for the topography of the cell and an average elevation for the stream stage and the stream bed elevation, that's going to limit how well those perform. So simplification basically means limitations. The third thing is the limitation on how the models should be applied or used. It's important to remember that these are regional scale groundwater models. Large cell sizes, typically a mile by mile. They typically are operating on 1-year stress periods. It's also important to remember that these are, again, regional models. They are calibrated and evaluated regionally. Some areas within the model domain may perform better than other areas, and the model may still, fall within a calibrated model. The last point is to remember that a well-calibrated model doesn't necessarily mean it's going to give you accurate predictions, especially with these GAMs as you're starting to use them in a predictive mode to model stresses, pumpage, beyond which they were calibrated for. If you're trying to evaluate how a model is going to respond to a significant pumpage stress, and you didn't have any pumpage stress near that in the historic calibration time period, the well-calibrated model may not necessarily give you an accurate prediction. So you need to just keep these all in mind when you're looking at your model results and how you're using them, and remember that there's a lot of limitations, and you really need to understand those.
I appreciate that, Andy, and so we're getting close on time here, and I want to give each of the panelists here an opportunity to share a closing thought. And Natalie, if I can start with you, do you have a thought you'd like to leave with the group here?
Yeah. Andy, I liked your point that GAMs do not give you the answer, and that kind of ties into this talk about uncertainty. And I'm really looking forward to how we start communicating uncertainty to, and using it in joint groundwater planning, because really that communication of what that uncertainty is very important to actually understand what your answers are that you're getting from the GAMs. And I also say that, like John mentioned, it's great to have all these bells and whistles of new technology and new modeling capabilities, but we still really need the physical understanding of an aquifer and the data to support that, because like Andy said, garbage in, garbage out. And just one last thing, for everyone in the audience, I would encourage you all to get involved in model development. We have stakeholder advisory forums for all of our model updates, and if you want to kind of learn more about what they are and what this uncertainty is and what those limitations are, that's a great avenue for that. So that's it.
Thanks, Natalie. John, any final thoughts?
I agree with what Natalie said and Andy from earlier. I think the conceptualization of the aquifer in the system, it's key, and it comes down to that building in that knowledge of that system, into the model, making that in as best you can. And the best model doesn't make up for issues with conceptualization. And I think it's important to get an estimate on the reliability of those simulated outcomes using, again, some form of uncertainty analysis, and kind of capture the range of what simulated values could be versus just that result, the result. And I think that's valuable information for everybody, for the public, for stakeholders, and for the regulatory entities.
Okay, appreciate that, John. And Andy, any final thoughts?
Yeah, just want to reiterate being careful how you use the model, be aware of the limitations, uncertainties associated with them, so you can really kind of understand what the model is telling you. I realize the name of the panel is the next generation of GAMs, but a lot of the next generation of GAMs is going to be not associated with new modeling techniques or things you can do with the model. They're going to be really associated with data collection. I mean, we're talking to a lot of district managers. We're talking to people that can be on the ground collecting data. GAMs, as I talked about before, these are models based on data. Our understanding of the groundwater flow system is based on the data we collect. The ability to build and calibrate a model are based on the data that we collect. And so, I'd like to see more emphasis really on the data collection. I think that's important. I mean, there was a talk at the Texas Aquifers Conference last month on the Blanco River hydrologic modeling conceptualization, and there they lamented the lack of state funding for projects like that. And I'd like to see some more state funding, whether it be from the board. The board would be the natural one for projects like that. I mean, right now, all you can really do is suggest a project. If it's selected, then it kind of becomes a board project, and you can bid on it. I think it would be a good idea to start to recognize that there are groups out there that are wanting to do basic aquifer studies that are important, and provide some funding to them. I think that's something I think we should see more of.
Great point, Andy, and I appreciate you making that point. For my closing thought, for better or worse, the four of us here on the call spent a lot of time wrestling with groundwater models and trying to make sure that they're useful tools for many of the people that are listening in. And so, Natalie, Andy, John, I appreciate your time today. I appreciate you guys sharing your experiences and thoughts on where things are headed. And with that, I think this is where Leah pops in to bring the question.
I'm magically up here. Okay, wonderful. Well, a couple of the questions that actually came in, I don't know if to give credit to the panel or to our audience for basically anticipating Andy's closing thoughts. But there was one part, a couple questions came in, and one that you didn't quite hit on that maybe you could follow up on is there a specific type or format of data that is missing or that can be easily gathered for GAM utilization?
I mean, I'll just a lot of the basics. The type of data. I mean, as I mentioned in my talk about limitations, I mean, one of the problems we've had and continue to have is historic pumpage, and that's such an important parameter going to these models. Coming up with or starting to collect good pumpage data, for example, for a groundwater district manager, a good data collection of pumpage in your district, and then also be thinking about how you might look back and evaluate historic pumpage and be able to start refining that, methods that you might be able to start refining that, how much irrigation pumpage occurred in past decades, how can you figure that out? I mean, these are things that modelers spend a lot of time, money, and effort on is trying to develop those historic, pumpage data sets, because, we can collect all the data we want. If we get it perfectly from now on, in 2030, we'll have 10 years worth of data, but we're still going to be calibrating these models based on decades past. So we need to be looking at that, and then just collecting water level data, collecting a lot of the baseline data, organizing any pump tests that you might have heard of, that your stakeholders in your district might have conducted, so that if a person coming and developing a model says, "Hey, I need pump test data," you have a lot of the data for your district. I mean, just things like that.
Leah, I'd like to add one thought actually to that question. So with some of the groundwater districts that we work with, they've found opportunities to sort of hit two birds with one stone as it relates to data collection. There sometimes when a large permittee comes in, there has to be a bit of a hydrogeologic evaluation that's done that might include a pump test or an aquifer test of some kind. Whether it's the permit applicant putting in a monitoring well or the district monitoring an existing well, sometimes that provides the opportunity to get some of the really useful information for GAMs, like estimates of transmissivity and hydraulic conductivity. And then if you're using more than one well, you can get estimates of storativity, which is, to get to the slide that Andy showed with the very limited points of hydraulic property data. That's a way that you can start to infill and influence how models are developed in your own district.
It's a good practical suggestion. Another question that came in, Natalie, this one was directed at you. How does the development board foresee moving forward with probabilistic modeling that you mentioned?
I think that we're looking to, and John was talking a little bit about probabilistic and deterministic stuff. So I think we're going to kind of see what happens with that and how we can incorporate it in our models. But unfortunately, I don't know the details of that because I'm not a modeler.
Absolutely, absolutely. Okay, I'm just going through these. I'm trying to find one that we've got a bunch here, but I want to find one that's a little more broadly applicable. So there are two that basically are asking the same thing, but in opposite ways. There's a question saying, so are the GAMs good for anything? And then the other one says, but aren't the GAMs still the best available science? So I don't know who maybe wants to start with tackling those, and that maybe is a good one to end on.
I'll just start saying that they are the best available tool that we have currently for the purposes of joint groundwater planning.
I mean, they provide a good, I think they provide a good a platform to kind of assemble and put forth what you currently know about aquifers. They also provide a kind of give you an idea of what types of data and what parts of conceptual model for groundwater flow that you might need to be working on and thinking about. As Natalie said, they're considered to be living tools. The amount of data that we have, our understanding of the aquifers, the types of things like refining the grid refinements vertically and laterally to start incorporating groundwater surface water interactions a little better. These are all things that can be incorporated over time. But no, like I said, they don't give you the answer, they give you an answer. I mean, that's going to be the case with any model. And so you need to kind of understand the limitations, the uncertainty to be able to properly put the correct weight on and understand and interpret what the model's telling you.
At the risk of sounding defensive of GAMs, I want to address the "are they good for anything" question directly. And of course they're useful tools. If you think back to the hurricane piece, we know that they're wrong, and we're trying to have a nuanced conversation. If your takeaway from this panel is the GAMs aren't good for anything, I'm sorry. We should have presented it better, but they're useful tools. But it's important for us to understand their utility with a clear eye of their limitations as well.
Wonderful. Well, thank you all.